Do we have on Zoom? Good.
Yep.
Started. Should show up here. The same thing about the recording. Okay. Okay. Good. Hello everyone. Today we have Sharon Li that he will present HaloScope, harnessing unlabeled LLM generations for hallucination detection. Son is a final year PhD student here at UW, and he's advised by Professor Sharon Li. And his research interests lie in reliable machine learning and the applications to foundation models and AI safety. And we're very happy to have him here today. Son, go ahead.
Yeah, sure. Thank you for the introduction. So, hi everyone, my name's Sean, and I'm currently a fifth-year PhD student in University of Madison, and I'm very happy to here to present our recent works on language model hallucinations. So, yeah, without further ado, let's get started. So first, before diving into the technical details of this project, I would like to introduce you some of the background of my research to help you get a context. So my PhD journey really starts from the observations that the current AI system are versatile. So this AI system right now has already transformed a lot of new applications by taking a vast array of diverse kind of input data and then perform tasks like information extraction, sentiment analysis, and object detection. And definitely a lot of new tasks here. But this kind of progress has also comes to the challenges related to how reliable these machine learning models are when they actually deployed in the real world settings, especially considering this diverse data these models can subsume. So for example, my recent works tries to uncover this safety vulnerabilities of machine learning models for this self-driving car applications. So for example, in this slide shown, this self-driving car model can sometimes fail to identify the strange objects on the highway, like a moose, without alerting the human drivers. So this kind of a lack of awareness to unknown situations can be a very high, can be a serious risk in practice. So my PhD research really contributes to building safer and more reliable AI system that can better handle these uncertainties. So specifically, I work on developing both theory and algorithm in order to teach machine learning models what they don't know. So this is to say, I want to teach machine learning models to recognize and better respond to the data that they have never seen before. So this kind of research aspect is especially important in real-world settings where the unknown auto distribution data can occur at any moment. And having talked about the vulnerabilities in the input side, so my recent works has also explored the vulnerabilities in the output side. So this is especially important considering now people are more increasingly become interested in utilizing the generative foundation models for helping their critical decision-making in the real world. So that leads to the second part of my PhD research, which really focuses on responsible foundation models. So my research actually tries to identify and mitigate the safety vulnerabilities for the foundation models by hopefully tackling issues like language model hallucinations, bias and stereotype generation, toxic language, etc. So this talk, I'm going to focus on a specific work that tries to tackle language model hallucinations. So this is a joint work with Professor Sharon Li here in UW-Madison, and this paper is going to be a spotlight presentation in NeurIPS this year. So I would like to first talk with you a little bit about the background of the research. So what is the hallucinations for language models? So as shown in these slides, it's a very nice survey paper actually points out that the hallucinations for language models are actually the settings where language models can occasionally generate this seemingly plausible content, but either diverges from the user input, contradicts from the previously generated context, or misalign with established world knowledge. So here you can show a very interesting example. The language models are trying to say the tomatoes are actually rich in the calcium, but they're actually not. So this kind of like generations are called hallucination. And turns out that current foundation models can often hallucinate. So if you take a look at these slides, so the current state of art, like capable foundation models, like the OpenAI O1 model and GPT-4 model, they can even hallucinate with a high percentage of over 1%. So this, like if we directly make this falseful information directly delivered to the users, it can really sacrifice the critical decision-making process. So my research and my project tries to ask the question in here is, can we actually detect hallucinations before delivering the information to users? So you can think of, oh, there's a very typical solution for hallucination detection is, can we actually just do supervised learning, right? So the very typical process is, oh, we firstly have a bunch of input prompts. We're trying to prompt the language models to get some generations. And then hopefully we can recruit some experts like to distinguish, oh, whether this generation are true or false. And then once we get these annotations, we can just train a very simple true versus false classification model. And then in the test time, we hope this model can distinguish true and false for whatever generations the model can produce. Oh, there's a question.
So this is like in the example you said here, if you're having humans annotate, you're just having them annotate whether the LLM give a correct answer or a wrong answer or true. Because like, yeah, what are you having them annotate?
Yeah, so the question is, what annotations do we need in order to produce the hallucination detector? Yeah, so the annotation we need is whether the generation is true or false.
Not whether it hallucinates. Because you can, for example, I can ask you, give me a recipe for dinner, and then it responds back and says, here's a recipe for lunch. It's a nice steak. And technically, it didn't say anything wrong, but it hallucinated.
Oh, that is a good question.
Was that true or false?
Yeah, so in this project, we specifically focus on the hallucination that misalign with the established knowledge.
So the example I gave would be true or false? True.
It's so yeah, I think it's false. In terms of the so it contradicts with the user instructions.
Okay. So
But here,
3 criteria. And ask it whether messed up in any of those 3 criteria.
Actually, in this project, we specifically focus on the data that falls into the third category, which is the contradiction or non-contradiction with the established world knowledge. Yeah, but definitely this kind of approach can apply to other like criteria. So yeah.
Okay.
Yeah, thank you for the question. Yeah, so yeah, after this kind of a training, we can get the supervised classifier on this. But it turns out that this requirement on this like curated data set is very costly to prepare and not easy to adapt, considering the evolving landscape of the language models people are developing these days. And also these language models can generate a bunch of diverse outputs. So it might be harder to like recruit like annotators to do this. So the key research question that our paper tries to answer here is how to mitigate this strong assumption on human annotation. So here, so our paper HaloScope actually tackles this problem by utilizing the unlabeled data. So following the previous setting, so if we prompt the language model to get a bunch of generations, so we can typically like regard these generations as an unlabeled source of information. So we record that in the previous slides, we have shown that the language models can generate which hallucination ratio of 1%. So that means if we model this unlabeled data generations with this mixed distribution of both true and false information with a ratio pi here denotes the hallucination ratio. So the pi here for the OpenAI O1 model could be 1.4%. So this is a model we are actually proposing here in order to recognize the unlabeled data set that the language model is generated. So given this unlabeled data set, a very natural question to ask is, can we actually separate truths from hallucinations given this unlabeled data set? So if we can do this perfectly, then we can, so the following step will be just train a classifier based on a perfect separation in order to perform test time inference. So the key step that we're trying to utilizing here is we are trying to estimating the membership of the unlabeled data set using language model representations. So given this unlabeled language model generations, we firstly feed these generations to the language model itself to get their representations. And then in this representation space, we can perform principal component analysis in order to extract the hallucination subspace, which naturally consists of first K several like principal components, and then we're like projecting the unlabeled data representation matrix to this extracted subspace in order to get an average score for membership estimation. And we hope there's a separation in this score space. But you might wondering why there should be a separation in the scores, within the scores, right? So here we actually provide a very simple mathematical interpretations based on our membership estimation score. So consider a simple case where we projected the embeddings to the first principal component and then record that pi, which is a hallucination ratio of the unlabeled data representation matrix, is very small. So the first principal component first step in principal component analysis is really tries to subtract the mean embeddings of the unlabeled data representation matrix to each of these representations in the unlabeled data set. So that now the true representations, which is colored in orange, these representations, which are subtracted by this mean vector, should be closer to the origin because pi is small. And then in contrast, this hallucinating embeddings, which are colored in purple, should be further away. And then also record the definition of how we calculate the first principal component is to maximize the variance after projecting the embeddings to this principal component, so that this principal component should ideally pointing to the direction where the variance is maximized after projection. So this should point, the direction should point into the hallucination embeddings. So in this way, the scores for the hallucination should be separated from the scores for the truthful embeddings. Okay, yeah, a question.
So just to understand, when you say projecting the embedding, you mean the representation before you apply the softmax, or like what exactly?
Yeah, so the question is, how do we exactly do the projection? So the projection is by directly doing the the dot product between the.
I'm asking what do you use to, like, which embedding do you use? Like, is it the representation that the model outputs before like the softmax predict the probability distribution?
Okay, yeah.
Or
Gotcha. So the question is, like, which embeddings are we use in order to calculate the score? So in implementation, we actually explore different locations in order to extract the embeddings. Because the language model typically has multiple layers, and then we try to extract the representations from the layer output for each of these layers. And then inside each transformer layer, there are specific locations such as the transfer attention output or the output of the multi-layer perceptron. So we for 3 different locations for each transformer layer, and then like do ablation studies, which is included in our paper. So if you're interested, please feel free to take a look. But the general trend is the language models tend to encode the truthful or hallucination information in the medium layers, and then different kind of model families, they actually perform differently in terms of how we choose the locations for like performing this score estimation. Any other question?
Can you just explain this again? I'm a little bit confused. Maybe let me say what I'm thinking is going on. So all these dots, these colored dots, are different samples, right?
Yeah.
And some of them are hallucinations, some of them are true. And then you're going to do PCA on this simple data set. You're just going to line.
Yeah.
And then you'll take a new data set and project onto that first principal component.
Yeah.
And then if it's bigger than 1, you'll say it's hallucinating. If it's less than, sorry, if it's bigger than 0, you'll say it's hallucinating. If it's smaller than 0, you'll say it's true. Something like that.
Yeah. So.
Or you decide the threshold, I guess.
Yeah, there should be a threshold which I'm going to introduce in the next slide.
And the idea is that it should be separable with respect to this principle.
Yeah.
So when you extract one Unlabeled, do you extract like the last order representation of the response of the model? Or so you give the model and input, the model is multiplied out and says response, right? So I guess you pick one of these objects as the value. So do you pick the last one, or is that also something you search over?
Yeah, in practice, we actually use the last token value, which is the I guess the common thing researchers do in literature. Yeah.
Why did you choose PCA for this variance maximizing?
Because firstly, PCA is unsupervised learning approach, so that is well. Yeah. And then secondly, because PCA has this interesting property here for how we're calculating the first principal component in order to get a separate score distribution. But we are definitely interested in exploring multiple choices in order to choose different techniques in order to get the truthful or false information direction. So I remember there's already literature that tries to explore semi-supervised learning. They actually rely on a very few shot label data set in order to firstly identify the direction and then performing this unlabeled separation afterwards. So that could be a very interesting direction to explore. Yeah.
But my question is, PCA is just linear model, so it is not that representative. So you might be able to use autoencoder or VAE. They are more powerful.
Yeah. That could be another interesting direction. So using this unsupervised encoder, we can extract some salient or meaningful direction in the latent space. But I personally think that would require some specific design in the latent lower dimensional space in order to capture the truthful information. Yeah, but I do recall there's a paper on utilizing sparse VAE in order to find these useful directions for downstream language model tasks.
So what is the original dimensionality of the sample?
So right here, because we are using the Llama 2 family when we're implementing the system, so the dimension is 1024 for the 7P model.
Okay.
Yeah. Other question? Yeah.
And this seems like, maybe I never heard of this, but it seems like kind of an idea you can use for any type of classification problem, unsupervised classification. You have two kind of classes, but you don't know the labels, so you do PCA and then you pick the threshold, whatever. But does it have any assumption that the two classes are linearly separable or anything like that?
Yeah.
Yeah, so the question, I think that's a great question. So the question is, do we need any additional assumption in order to perform this task? Yeah, I do think we need like implicit assumption on the ratio of pi, because if pi is not small enough, then this kind of interpretation does not hold, because like after subtracting is like the vector is a truthful representation might not necessarily close to the origin, because yeah.
So as pi gets bigger, to like bigger up to like a half.
Yeah, that's my hypothesis. Yeah, thank you so much. Okay,
I have a question.
so yeah, so
Hello?
and then this
Hello?
figure actually shows the like practical verification we're performing using the real world question answering data set. So we do observe a separable space in terms of the score estimation results. There's a question in the chat.
Yeah, can you hear me? Can you hear me?
Hello?
Hello, can you hear me?
Yeah.
Sure, yeah. My question is so you said that the middle layers is best in terms of doing such classification, right? I wonder how many attention heads do you use? You use all the attention heads and you just get the mean feature of all those heads for with respect to the last token. This is how you compute the feature.
Yeah. So the question is how do we utilize the attention features? In practice, we follow the previous literature that tries to utilize the concatenated attention outputs for calculating the truthful direction.
Okay, concat the feature from all attention heads. Okay.
Yeah.
Yeah, I also wonder a simple baseline in this case would just be feed the your question to GPT-4o and let GPT-4o do a binary classification, right? In this case, we do not need to worry about how large your epsilon or pi here is, right? Your data set can be extremely imbalanced. Yeah, I wonder in this case how good can GPT-4o perform?
So could you repeat the first part of your question?
Yeah, sure. So your question is just that give a user question and model's response. The task is to do binary classification, right? The model hallucinate or not. So a simple baseline I can think out is that you just copy paste your task here to GPT-4o as a prompt, or to any language model as a prompt, and ask GPT-4o to do classification. Yeah, I wonder how good GPT-4o is in this case.
Yeah, so the question is, can we utilize language model itself in order to do this true and false classification? Yeah, we do have a very strong baseline in the paper that tries to directly prompt the GPT models. And then we found that this kind of very like the current capable models cannot actually produce like correct predictions. So I think that could be related to the overconfidence predictions for these language models.
Okay, thank you. Yeah, that's truly helpful.
Yeah, thank you. Okay, so then the final step in our approach is to really do training the hallucination classifier based on the separable score distribution. So here the trick is, as I mentioned, here we have a threshold T, which should be determined on a separated validation set in order to get the proxy training labels for this unlabeled data set. So then after we get the proxy labels, we can train very simply using this 0-1 loss, which is like instantiate in practice as a sigmoid classification loss for training. And then after training, we can just do this hallucination detection in the test time.
Wait, so you train to find your threshold.
What's your question?
So like
Sorry.
your PCA thing reduces it down to one dimension,
Mhm.
it's only on one D, and then
Yep.
trying to find the threshold to discriminate, right?
Yep.
So you are using labels, right?
So
To find that threshold.
yeah, so the question is, do we need labels in order to find the threshold? Yeah, we do. We need the label validation set in order to determine these hyperparameters. Yeah. But in practice, we only use 100 question and answers, and then they're ground truths in order to determine the threshold. So 100. So this should not be a very high, like strong requirement in practice.
Okay. Yeah.
Cool. So like I'd like to right now introduce some of the experimental results. So we actually evaluate our approach in basically the truthful the question answering data set, which follows closely with the experimental method in the literature, where it tries to get this training, validation, and test splits by utilizing the 75% of the data set as the unlabeled data set, and 100 of them as the validation set, and the remaining of the data set is used for testing. We actually tested our open source models, which are Llama and OPT, and then so here in these slides I'm going to show off our results. So here we're comparing with a bunch of like representative hallucination detection baselines, which consists of like uncertainty-based approach, like a perplexity entropy-based method. And then we also compare with the GPT-based approach, such as self-check GPT and verbalize and the self-evaluation approach. And then we are also compare with this unsupervised learning approach, CCS, which is very closely related to baselines, and found that our approach can outperform all of these like competitive baselines, but without additionally sampling step in order to estimate the truthfulness for the generations. So it could be like efficient and effective in practice.
So why single sampling input?
So the question is why single sampling is important. So there are a bunch of like baselines in literature that tries to prompt the language model in order to generate multiple answers for a single question, and then calculate some scores based on the multiple answers in order to estimate whether these the answers are true or false. But so the one intuition they're relying on is if multiple generations from the language models are not consistent, then that means this generation probably is going to be like false. So yeah, that's their intuition. Yeah.
So it assumes LLM produces the correct answer with a high probability and generates incorrect answer, hallucinated answer with low probability, right? And then we compute the
So are you
recipe to
Yeah.
distribution.
are you asking the baselines or
Yeah, 100%.
Yeah. I guess that's the their general intuition behind their message. Yeah. Other
I'm
question?
sorry. Can you go back to the last slide? I'm still confused on how you're thinking, the one before that, where you were, the one before. Yeah, what's going on here? How are you picking the threshold? I'm still confused. So you're not using labels on your training data.
Yep.
But you are using a validation set
Yep.
that does have labels.
Yep.
So what you do is you found your PCA direction, right? You have that vector.
Mhm.
And then you take samples from your validation set and you take another product with that principal component vector, gives you a number. And then using your threshold, you decide whether that's, you do 0, 1 loss with that. And then that's how you tune your threshold parameter, is that right?
So the question is, how do we do the validation? So the general approach is we're actually calculating the scores based on the unlabeled data set only. And then, so the threshold here is a hyperparameter. You can think of as just a value. So once we get this value, say a random value, and then once we get this threshold, we can get the label training set on this unlabeled data set. And then based on this threshold, we train a binary classifier on the unlabeled set. And then we're testing the performance on the validation set. How good is it is
Yeah, so
the
then
training
how do you search
classifier?
over the threshold? Usually for hyperparameter, you're using like grid search.
Yeah.
So is that what you're doing, just a grid search over threshold, or?
Oh.
Some kind of clever way of doing that?
Yeah, in practice, we're actually doing something similar to this. So we're like having 20 or we actually have 10 threshold. So like we're actually thresholding the source based on a 10% large and then 20% and until up until 90%. So that's what we're doing in practice.
Okay.
Yeah, but definitely you can like search in a more fine-grained way in order to get the more accurate labels.
Okay, I think I get it, yeah, that's, yeah, so it really is unscripted, because none of your training data. is-
Yeah.
Okay, all right.
Okay. And then, yeah, one last thing I want to mention for our approach is the HaloScope can actually generalize across different data set. So imagine if we, like in practice, this unlabeled data set can be very different from the generations in the test time. So what about we actually train a classifier, extract the direction on a different unlabeled data set from the test set. So this plot actually shows that our approach can able to generalize to different distributions, even when this like unlabeled data set are very different from these test sets, such as this truthful QA and trivial QA are just the question answering data set without context, but co-QA and tidy QA are this question answering task based on a long context. So that's our the basic design intuition. So we definitely can find more ablations on like which layer to use, which direction to extract embeddings in our papers. So yeah, and then finally, I'm going to summarize this talk. So in this talk, we already seen that this current AI system, they cannot produce like reliable predictions for this unknown data. Especially the large language models, they can generate hallucinated content during interaction with the users. And learning with a supervised approach is effective, but suffer from this high annotation costs and the low flexibility issues. Our approach tackled this problem by harnessing unlabeled generations. And firstly, it estimates the membership of the unlabeled dataset and then train a binary classifier afterwards. So thank you for your time, and we're happy to take your question. Yeah. Thanks so much.
So it's not really trading though, it's just two data hyperparameter. When you're trying to find the binary classifier.
I wouldn't agree it's all about tuning the hyperparameters.
No, I know, but like the training part means when you do PCA, that's the training part.
Yeah.
Sorry, yes, what training is that?
It's not.
Create the matrix, right? Which is just the representations basically,
Mhm.
and you don't know whether they're true, false, you just take the representations,
Mhm.
you just extract the PCA,
Mhm.
right? So there's no training there.
Yeah.
And then you extract only one direction or just the first component or?
Actually, the number of the direction we're utilizing is another important hyperparameters.
A lot of decisions.
Yeah.
So then, let's say after we extract the principal components,
Mhm.
then you take a validation set, right? Which you know, like these are 0, these are 1, truthful, not truthful. And then you just find the linear classifier, basically, right?
Yeah.
That fits your validation set.
Yeah.
Yeah, and is your set, your validation set balanced, like 50% and 50% or?
So the question is whether the validation set is balanced. We actually, in practice, we don't require like a specifically designed validation set. We just randomly sample 100 questions and get their generations and label them.
But what if like 99 are with the really ones, non-truthful, right? Like this is. Yeah.
Yeah, that could be a very interesting like observations to explore, but we haven't we haven't like take a very close look at the validation set. We just assume we can do this very simple random sampling to get the validation set.
So why can't you just do like, instead of using 0, 1 loss, use something that's differentiable, like logistic loss, and then do 1D binary classification on your validation set, and you'll find the perfect threshold.
Yeah, so the question is whether we can use 1D classification. Yeah, that's actually a very good question, and it's actually brought up by the reviewers. So my personal thought is, if we're doing a 1D classification, it's actually essentially like a threshold-based classifier.
And that's what you're trying to find. You're trying to find.
Yeah, but because we're training the binary classifier based on the representation so that representations can include more information rather than just one-dimensional score. So that's why we're trying to decide to use representations.
Wait. No, I'm saying with the representation. You have your principal component vector.
Yeah.
And then you're gonna take, now just think of your validation set as your training data set. Basically, you're gonna take each sample from your validation set, hit it against your principal component vector. That's gonna give you a number. And then you plug that into your loss, and you find the optimal threshold for all the vectors that are projected onto that principal component. Like this is after you. Like I agree, using the representations is good and all that. I'm just saying to find the threshold.
Oh, I
Why
see.
don't
I
you
see.
treat it as another learning problem. Like you can just train on the validation set.
Yeah, that could be actually training on the validation set. It could be more informative than
I mean, won't that find you the perfect threshold, assuming your data is linearly separable after you project it onto that principal component?
Yeah, I would like to say that could lead to the optimal threshold we can achieve on the validation set.
Yeah.
So,
But why wouldn't we just do that instead of treating it as a hybrid rather than doing grid shift or something?
yeah, that could be, I think that could be a very
But
interesting.
then the question is, are you cheating it?
Yeah.
Training, right? So
Yeah.
I don't know, I'm confused. But I think it's a good talk. It's an interesting idea. I'm just trying to understand. Yeah. But okay, yeah. Why? Yeah, you should try it. What happens if you just find the optimal threshold and your results look so much better?
Yeah. I think I can try, but that's going to be more involved than the current approach. Yeah.
Which algorithm are you using? Yeah.
Which
algorithm? Does SVD?
Yeah, just SVD.
It's 500,000 megabits. Okay, yeah, sure. Why not? But I don't know, but there can be some technical contribution for SVD. Is that you can, but you're just using the vanilla SVD.
Yeah, but you guys are working on a series for SVD. I'm very interesting to talk.
Yeah.
Whether we can further refine the scores, and then hopefully that can lead to more provable algorithm. Yeah.
Something that is in place, we did try to state the validation set. And to basically just find, the directions in which the negative sounds are and the positive sounds are. And then just project a new data sample in this direction. And see in which one is closer. You see what I'm saying? Like you just take the validation set and you just find the subspace in which the positive, even though it's small, it doesn't matter. Find the subspace in which the positive sounds are and the subspace in which the negative sounds are. Things will be like 50 dimensional, not similar to 50. And then taking a new sample and projecting it in each one of the subspace and see where it's closer. Like is there a separation already in the representations of the validation level?
Yeah, so the suggestion is to firstly get the subspace based on validation setting and then test it on the unlabeled set, right? Yeah, I think that's
that's a baseline because why doing the PCA and all these extra samplings if you by just having 100, even though get the same results.
Yeah, yeah.
Hypothesis was about hallucinations on kind of schedules.
But then it's a baseline, you know.
Yeah, but yeah, in practice, we don't want to do like too much thing on the validation set. Yeah, so that's our thought.
Yeah, but I mean, since you are using it.
Yeah. Yeah, we could maximize the benefits of the validation set. Yeah, I agree with that. Yeah.